Buenas tardes a todos y a todas y buenas noches a los que nos ven desde Europa. Me presento de nuevo para aquellos que no pudieron asistir a la inauguración del lunes. Mi nombre es Vicente Pérez, soy director de la UNED-México y orgulloso miembro del comité organizador del SINCA, que termina hoy. Porque ya llegamos a la recta final y me acompañan hoy la doctora Idania Cepeda, el doctor Luis Alfaro y el doctor Felipe Cabrera de la UDG. Como saben todos los que han estado con nosotros esta semana y tal como preveíamos mientras organizábamos este congreso, hemos experimentado toda la casuística de posibles problemáticas y, sin embargo, gracias al esfuerzo de los compañeros que han hecho de moderadores, de los estudiantes, que han hecho de productores y, por supuesto, de la excelente disposición de los propios ponentes, hemos conseguido superar cada uno de ellos, así que muchas gracias a todos. Pero lo más importante para nosotros, sin lugar a dudas, ha sido el número de personas a las que hemos podido llegar, uno de nuestros principales objetivos. Y desde luego les puedo adelantar que se ha cumplido y muy por encima de nuestras propias expectativas. Pero justo de eso nos va a hablar el doctor Luis Alfaro, a quien cedo ahora mismo la palabra. Doctor.
Gracias, Vicente. El día lunes tuvimos 1,112 asistentes. El día martes tuvimos 687 asistentes. El día miércoles 526 asistentes. Y el día jueves tuvimos unas visitas de 410 personas conectadas. Estos son números mínimos porque la plataforma que utilizamos, Teams, nos permite solamente detectar las cuentas de las personas que se registraron, ¿no? Propiamente con un correo. Entonces, tenemos la impresión de que los números, a pesar de que son bastante altos respecto a otras ediciones, pues todavía son más altos de lo que los estamos reportando ahora, ¿no? Tenemos también un registro de las visitas o visualizaciones de diferentes partes del mundo. Les comento que recibimos visualizaciones de 17 países diferentes. El que más nos visualizó fue, obviamente, México, seguido de España y, en tercer lugar, Estados Unidos. Pero me gustaría destacar, además, que tenemos visitantes de partes que no esperábamos. Por ejemplo, Alemania, tuvimos visitantes de Irlanda, tuvimos visitantes o visualizaciones, mejor dicho, de Brasil, de Italia, entre otros países, ¿no? Llegamos a bastantes países de Centroamérica que no habíamos contado con participación en SINCAs previos. Entonces, estamos muy contentos porque de verdad fue pues una edición diferente y nos permitió de alguna manera aprovechar la tecnología para expandir el alcance que tenemos normalmente, ¿no? Ya cerrando con la parte de los números de las visitas y visualizaciones, me gustaría comentarles que el SINCA entrega constancias a todos los ponentes que participaron y de eso me voy a encargar yo en las próximas semanas. Les voy a pedir pues mucha paciencia, 3 semanas más o menos como máximo voy a tardar en enviar a sus correos con la información que nos permitieron registrar en la plataforma. Todas las constancias, ¿no? Si hubiese algún problema de orden de ortografía o cuestiones por corregir, yo estoy pendiente del correo y pues vamos a estar en comunicación para solventar lo más rápido que se pueda cualquier problema, ¿no? Agradezco entonces pues a todos por haber participado en este SINCA y cedo la palabra de nuevo al doctor Vicente Pérez.
Muchas gracias, doctor Alfaro. Bien, una cuestión que también queríamos anunciar, que el Congreso recibió este lunes la certificación CIAC, el Certificado Internacional de Análisis de la Conducta. Este reconocimiento es otorgado por un comité formado por los responsables de diferentes instituciones independientes que, sin ánimo de lucro, pues certifica que el contenido de una actividad se ajusta perfectamente a los principios del análisis de la conducta. Y así, de hecho, las constancias de participación de este año, de las que nos hablaba el doctor Alfaro, van a contar con este sello de manera adicional. Bien, en breve le cederé la palabra al doctor Cabrera, que se encargará de presentar al doctor Galizio, un ponente de excepción para la conferencia de clausura que cerrará esta 8ª edición del SINCA. Pero antes queremos ceder la palabra al doctor Hugo Reyes, de la Universidad Autónoma de Aguascalientes, donde, si todo va bien, se celebrará la siguiente edición, la 9ª. Doctor Reyes, buenas tardes.
Hola, ¿qué tal? Buenas tardes. Un saludo a todos, me da mucho gusto poder verlos. Pues, ¿qué les puedo decir? Para mí es un honor poder participar justamente en la próxima edición. Nos ha tocado participar ya presentando algunas cosas, colaborando en distintos aspectos, pero va a ser la primera ocasión que nos toca por ahí sumarnos a la organización del evento. Yo tengo harto cariño por el SINCA, entonces para mí es un gran gusto que esta situación pueda ocurrir. Entonces, pues nada, derivado de esta situación, pues será un enorme placer poder verles la cara, poder estrechar sus manos y, ¿por qué no, poder tomarnos una cerveza? Los esperamos aquí en la Autónoma de Aguascalientes y un saludo y un abrazo fuerte para todos. Gracias, Vicente.
Muchas gracias, doctor Reyes. Bueno, pues como pueden comprobar, ya ponemos nuestras miras en la novena edición del Congreso. Sin embargo, este Congreso, el octavo, no termina aquí. Les recuerdo a todos que en los próximos meses seguirán subiendo tanto a la página oficial de SINCA como a la sección dedicada a este Congreso en la web de la UNED-México las distintas grabaciones de todas las sesiones que se han celebrado esta semana y les sugerimos que estén atentos a nuestras redes sociales donde haremos los diferentes anuncios. Y, por supuesto, desde esas mismas redes sociales también anunciaremos la publicación y la disponibilidad gratuita del volumen tercero de Aproximaciones al estudio del comportamiento y sus aplicaciones, el libro del SINCA. Y del contenido del libro nos va a hablar a continuación la doctora Cepeda. Doctora Cepeda, tiene usted la palabra.
Gracias, Vicente. Bien, bueno, yo quiero compartirles que, pues, a lo largo de, como ha sido ya tradición para los seminarios del SINCA, pues en esta ocasión también trabajamos en la edición de un libro que ya se suma a los anteriores, siendo pues ya la séptima edición. En este caso, el libro del SINCA pues será publicado en enero de 2022 y, como mencionaba Vicente, pues a través de las redes sociales estaremos informando para que ustedes puedan acceder y descargarlo. Quiero compartirles que este volumen está conformado por 17 capítulos que incluyen propuestas teóricas, revisiones, trabajos empíricos y trabajos aplicados. Algunos de los trabajos son representativos de las ponencias que presenciamos, como el capítulo de Marta Peláez y su coautora Hayley Naming, o bien el capítulo de Ricardo de Pascual, del cual tuvimos ayer una conferencia. Los autores del resto de los capítulos pues son de distintas universidades, entre ellos de la Universidad de Guadalajara, de universidades españolas como la Universidad Autónoma de Madrid, la Universidad Europea de Madrid, la Universidad de Córdoba y la Universidad de Jaén. Participan también de la Universidad de Sonora, de la Autónoma de Aguascalientes y de la Florida International University, Endick College y Shabana Institute. Y bueno, nada más les recuerdo pues estar pendientes del anuncio y los invito a que pasen a la página de seminarioscinca.com, donde pueden descargar todos los volúmenes anteriores y donde vamos a colgar también esta nueva edición. Muchas gracias.
Bien, no metiendo más y ya dejo paso al doctor Cabrera, pero no sin antes agradecer de nuevo al SINCA por darnos la oportunidad a la UNED-México de participar en este evento y en esta experiencia, de la que ya les aseguro que hemos sacado muchos aprendizajes que nos gustaría aplicar en futuras ediciones. De nuevo, muchas gracias a todos. Les esperamos en Aguascalientes y, doctor Cabrera, tiene usted la palabra.
Bueno, pues muchas gracias también por estar participando en esta ceremonia de clausura. Y precisamente cerraremos con broche de oro con el doctor Galizio, que justo dará en este momento la conferencia. Y antes de ello, quiero hacer una presentación, la haré en español brevemente. Solamente decir que el doctor Galizio, bueno, nada más ni nada menos que actual editor del JEAP, nos acompaña, y él estudió su licenciatura en Kent State University, haciendo sus estudios de la maestría y doctorado en University of Wisconsin en Milwaukee. Él expresamente señala que su interés está ligado completamente al análisis de la conducta, pero con áreas de especialización en la farmacología conductual y cognición comparada. Con eso, las iniciales forma en su laboratorio ABC Lab. Entonces, la trayectoria del doctor Galizio obviamente sería muy extensa aquí señalarlo. En Internet pueden fácilmente encontrar su currículum y ver la cantidad de escritos, participaciones en eventos y premios que ha sido acreedor. Solamente mencionar que él se centra actualmente en investigación vinculada a la memoria y sobre el concepto de aprendizaje, ¿no? Además, el estudio de los efectos de la droga en conducta compleja y en el área, como les comentaba, de la cognición comparada, buscando de manera muy interesante las rutas de la conducta conceptual humana en especies no humanas. Añadidamente a esto, bueno, hay un libro que se acaba, bueno, hace algunos años se reeditó, hecho originalmente en 1991, ahora en 2015, precisamente sobre drogas, uso y abuso, del cual, bueno, también hay disponibilidad en diferentes medios para conseguirlo. También ha sido parte del miembro editor de la revista mexicana de análisis de la conducta. Así es que su participación en México se extiende más allá de solamente esta presentación. Él ha visitado en numerosas ocasiones México, le gusta mucho, de hecho, justo unos momentos había preguntado cómo estaban por acá las cosas porque tiene los deseos de visitarnos, eso le agradecemos mucho. Y cerraría con esta presentación con un detalle que me pareció muy interesante mencionarlo. El doctor Galizio mencionaba que tiene un seminario con sus estudiantes en donde tratan precisamente de hablarlo en español. Eso yo creo que es muy significativo para toda la comunidad y con ello sabemos que pues el interés por este idioma de muchos de nosotros que estamos en América Latina, en España, pues precisamente se extiende. Pues entonces, Professor Galizio, we are very proud to have your talk. So you have about 1 hour to show us your presentation. Please, if you call to initiate with turning on your microphone.
Okay. Thank you, Felipe. Can you hear me?
Yes.
Okay. Vale. So, primero, me gustaría decir gracias por la invitación de Felipe para hablar en esta conferencia SINCA. Me siento honrado por la invitación. Pero segundo, debo disculparme contigo. Cuando ustedes visitan en conferencias en los Estados Unidos, todos hablan inglés. Tengo frecuencia de decir esto, pero mi español no es suficiente para continuar. Entonces, con mi disculpa, voy a cambiar a inglés ahora. Okay. So my starting point is this question. Where do novel stimulus relations come from? Indeed, where do novel behaviors of any form come from? Answering this question has been a major challenge from the earliest days of behavioral science. Now, the way behavior analysts understand these issues changed fundamentally over 30 years ago with the pioneering work of this man, Murray Sidman, and the stimulus equivalence paradigm. His paradigm is really the starting point for the work I'm going to be talking about today. So, although I suspect most of you are familiar with this basic procedures, let me start with a quick review of the basics of stimulus equivalence. It all begins with conditional discrimination training with physically unrelated stimuli, arbitrary or symbolic, matched to sample. So, for example, we might present a green circle as a sample, and selection of the printed word green, but not blue, is reinforced. Alternatively, we might present a blue sample, selection of the printed English blue, reinforced. Generally, a second set of related conditional discriminations are trained as well. So, for example, we might present the printed word green. In that case, the selection of verde would be reinforced, but not azul. Or alternatively, the printed word blue could be the sample, and selection of azul reinforced. Now, the key to stimulus equivalence, of course, is that after training these four basic relations, a number of additional relations emerge. And these emergent relations include reflexivity. Sidman likes to use the mathematical set notation, so A equals A, or in this case, presentation of the sample green circle. Well, selection of a green circle would indicate reflexivity. Alternatively, symmetry. If A equals B, then B equals A. So we trained the green circle to the printed word green. Now, if the printed word green is presented as a sample, selection of the green circle would reveal symmetry. And finally, transitivity. If A equals B and B equals C, then A equals C. In this case, a transitive relation would be shown if, in the presence of the color green, selection of the Spanish word verde takes place. The emergence of these three relations is how Sidman defined an equivalence class. And although he was readily able to demonstrate the emergence of equivalence classes in children, in a companion piece to the classic Sidman and Tailby article, Sidman and colleagues, Rouse Lazar, Cunningham, Tailby, and Kerrigan, attempted to replicate the effects in animals, but they were unable to. Although monkeys and baboons learned the arbitrary conditional discriminations, they did not show emergent symmetry. Now, to many, this suggested the possibility that emergent equivalence might be uniquely human. Now, over the years, many kinds of behavioral or other phenomenon have been thought to be unique to humans. Tool use, for example, but then chimpanzees and actually other species have been shown to use tools. Fire, the use of fire has been proposed. A recent observation from Australia has shown that some corvid bird species are capable of actually spreading fire, and they use the bushfires to stir up insects that they can feed on. So fire may not be uniquely human. Language has been a controversial topic, and certainly many would argue that complex forms of verbal behavior that we call language are uniquely human. Of course, there have been a number of controversial studies with apes and others that suggest that at least some forms of language might be found in animals as well. Some have proposed that the ability to behave according to what others might experience, theory of mind, might be a uniquely human phenomenon. And some have argued that episodic memory, the ability to travel backwards or forwards in time mentally, is uniquely human. You know, the cognitive psychologist Paul Bloom, I think, summed it up with this quote. He said, "Philosophers have often looked for the defining features of humans, language, rationality, culture, and so on. But," Bloom said, "I'd stick with this. Humans are the only animals that like Tabasco sauce." Well, I presented this to a student group, by the way, and several of them sent me YouTube videos of animals eating Tabasco sauce. So even that may not be uniquely human. In any case, after Sidman and Tailby, there was an explosion, I think it's fair to say, of basic research with human participants that really changed the way that at least behavior analysts think about complex human behavior. This led to some new theoretical approaches to complex phenomenon. Sidman's theory, his notion was that classes include all elements of the reinforcement contingency, and so equivalence is an additional feature, a basic feature of the reinforcement process. But a subsequent theoretical development from Steve Hayes, you're probably familiar with relational frame theory. Hayes argued that arbitrarily applicable relational responding is a higher order operant that's developed by multiple exemplar training, and these abstract relational operants are responsible for equivalence and many other complex relational phenomenon. Pauline Horn and Fergus Lowe developed what is often considered sort of a third approach, the idea of bi-directional naming. That is, in infancy, humans learn to name objects, and in turn, the site or the stimulus object elicits naming, and this bi-directional operant then produces the essence of symbolic processes. In addition to these theoretical and empirical advances, it's been discovered that these equivalence phenomena have many applications, and today, indeed, they're widely used in skill training and also in higher education as well. But what about that search for emergent relations in non-human animals? Well, that has not gone so well. In fact, there have only been a few demonstrations of equivalence relations in animals, and it's been particularly difficult to demonstrate symmetry. Karen Lionello-Denolf in 2009 reviewed 24 studies with animal subjects. Only 2 of them showed anything like consistent evidence for symmetry. Kate Bruce and I have recently reviewed that literature, and then Karen Lionello-Denolf just published a recent review. But the conclusions really have not changed very much. It's been very difficult to demonstrate anything like equivalence relations in animal subjects. Now that sort of led some researchers like Steve Hayes to argue that perhaps, again, that equivalence or relational framing, as he would put it, is uniquely human. In this quote from Hayes and Sanford, 2014, Hayes argued, evolution science itself suggests that human symbolic behavior has unique properties. No non-human animal has yet shown the defining features of relational framing or equivalence, and the centrality of relational framing to complex human behavior is very evident. Perhaps unlike Tabasco sauce, this phenomenon of relational framing of emergent equivalence classes seems very fundamental to important human behaviors, verbal behavior, to say the least. Further, because of the uniqueness of these phenomenon to humans, Hayes went on in his 2016 chapter to say, at that point, animal laboratories were immediately less important. And this is, I think, an interesting point, because in that sense, it's certainly true. The development of research on stimulus relations is different from the history and the traditions in our field of behavior analysis. In our field, basic processes have traditionally been discovered and elaborated in the animal laboratory and then extended to human affairs. equivalence, relational framing seems to be different. But have we, in fact, identified basic processes in the human research on stimulus relations? Steve Hayes would say yes, and there have been some impressive studies. But I'm not sure that the origins of derived stimulus relations have yet been properly discerned in humans. There are some great studies, Martha Pelaez, Dermot Barnes-Holmes and colleagues, Carmen Luciano. All three of these research teams have trained in very, very young infants, trained relational frames or equivalence processes through multiple exemplar training in very, very young children. But even so, these children are verbal. And so I'm not sure that we're actually looking at the origins of these frames, because if the children have even some verbal behavior, then they've already developed some forms of equivalence classes or relational frames. Might the lack of the early experiences that we see in infants, in fact, make it difficult to test for equivalence classes that might yet be observed in non-human animals? There are a couple of research procedures, of procedural modifications that suggest this might be possible. One classic study was done with sea lions by Schusterman and Kastak all the way back in 1993. They used multiple exemplar training. They trained many symmetry relations in their sea lions and found emergent symmetry. But it's been very difficult to replicate this process in any other non-human animals. It's failed in chimpanzees, failed in pigeons, and a couple of recent studies from our laboratory, we've not been able to replicate the effects of multiple exemplar training in rats either. There is so not in rats. So another kind of approach or procedural modification originally was developed by Frank and Wasserman, and then it's been followed up by Urcioli and colleagues. And their modification in pigeons was to, first of all, to use successive rather than simultaneous conditional discriminations. That is a go, no-go type of conditional discrimination. I'll have more to say about that later. They also, in addition to the arbitrary matching relations, they also trained identity relations with the relevant stimuli. By training these things concurrently, they were able to demonstrate symmetry relations or something like symmetry relations in pigeons. What about rats? We've tried to replicate this in two studies, one that was published in 2015. Ashley Pritchard was the student involved with that one, and then in a paper that we just got the page proofs for, we were unable to replicate the Urcioli type effects in rats in that study either. So none of these procedural modifications have been very successful in producing effects with real generality. Perhaps the problem has to do with conditional discriminations. Non-humans, and this is supported by the Urcioli approach, it may be that animal subjects simply have difficulty abstracting stimulus objects from their physical locations and their temporal positions. There's evidence for this in pigeons and rats. So that takes me to a third procedural modification that has also been successful in producing stimulus classes, and that's the repeated discrimination reversals procedure pioneered by William Vaughan. He studied pigeons in essentially a go-no-go discrimination using projected stimuli. And his goal was to see if two sets of stimuli might be trained to produce functional equivalence classes. This would mean sets of stimuli that share a common response or a common function. And to really be, that would define a functional class, and to define a functional equivalence class, we would want to be able to demonstrate some sort of transfer of function. That is, if the function of one member of a class is altered, then the function of the other class members ought to shift without direct training. That's what would need to demonstrate to show the presence of a functional equivalence class. Now, the way Vaughan did this was with pictures. They were all pictures of trees, and in fact, he had 40 pictures of trees. I'm just showing a few of them here. And he arbitrarily designated one set, let's just call it set 1, as the positive set. Responses to any of these set 1 stimuli were reinforced, and arbitrarily the other set of stimuli were designated as negative. Responses to them were extinguished. There's no reinforcement for set 2. When the birds had mastered the discrimination, were responding at high rates to set 1, but not to set 2, Vaughan reversed the discrimination. Now responses to set 2 are reinforced, and responses to set 1 are not reinforced. And he continued this process, reversing and then re-reversing the contingencies every few sessions. Now the question is this: if functional classes have been formed when the reversed contingency is contacted for one member, we should see transfer of function to other members. Consider this graph to see what hypothetical results would be. First, if there are no functional classes without classification, and what we have here on the horizontal axis is the trial position of each of the stimuli immediately following a reversal. And on the vertical axis is the probability of being correct. Well, without classification, these triangles show the animal would always be incorrect. There would be 0 correct, because on each trial, the previous session, the reversed contingencies were in play. So responding on the basis of the previous contingencies, the bird would be incorrect on their first exposure to each of the stimuli. However, if functional classes had formed, the results might be different. They would still be incorrect on the first trial, but once having contacted the reverse contingencies with stimulus 1, there could be transfer of function to stimulus 2, so that now when encountering stimulus 2, the bird responds correctly. The reversed contingencies, the changed functions, have transferred. So even though the animal has not experienced the changed contingencies with stimulus 2, 3, 4, 5, 6, or 7, or any of these, still the bird is able to behave differently because of transfer of function. Now, you might not get transfer of function immediately on trial 2, but it should occur in order to demonstrate transfer of function at some point before the animal has to encounter the contingencies twice. So here are the results from Vaughan's study. It's a complicated graph, but really quickly, what he's showing on the vertical axis is the probability of being correct, and on the horizontal axis, the first day after a reversal. So if we just look at the top animal, the dotted, the black points indicate the percent correct either to set 1, in this case, that's this line, or set 2, that's this line. And notice on the first few reversals of the experiment, the pigeons were almost always responding according to the contingencies of the previous session, and therefore their accuracy was below chance. It was below 0.5. But as the experiment went on, at some point they began to respond at about 50-50 after a reversal, and then, particularly with set 2, as you can see up here, this begins to show some evidence of transfer of function. The birds are responding after contacting a few of the reverse contingencies. They're shifting their behavior to the other ones. And by the end of the experiment, notice it took as many as 50 reversals, but by the end of the experiment with both sets, most of the birds were showing transfer of function. This one, for example. So Vaughan's experiment was generally viewed as showing evidence for functional equivalence classes. However, many researchers critiqued the Vaughan study as not being sufficient to show Sidman equivalence. After all, Sidman's criteria of symmetry and transitivity cannot be demonstrated in the Vaughan procedure. An answer to that came back with the sea lions again, and a very, very clever study by Kastak, Schusterman, and Kastak. Essentially, they replicated the Vaughan procedure with 10 positive and 10 negative stimuli. But then they went on, their sea lions had already learned matching to sample. These are the same sea lions that I showed you earlier. After the functional classes had been demonstrated in the two sea lions, Rocky and Rio, they then transferred those same stimuli to a matching to sample procedure. And they were able to demonstrate using match to sample arrangements that Sidman equivalence would actually show with these same stimuli that had been trained with the functional class technique. And so that convinced many researchers, including Murray Sidman, that in fact these functional classes established using Vaughan's procedures, that essentially these functional classes, if properly tested, can also show the same properties, symmetry and transitivity that we're looking for in equivalence classes. So these are very promising studies, Vaughan with pigeons, Kastak and colleagues with sea lions, but there haven't been replications with other species. I only know of one other study that was by Bill Doobie with rats, and it was not successful. It would be very valuable to replicate these kinds of effects with other species, and particularly, I think, in rats. One problem is that most studies of stimulus relations with rats have generally used visual stimuli. That might not be the best modality to use with rats. I don't know if you are familiar with the, we call in English a nursery rhyme. It's the three blind mice. The idea is that rodents are not very good in the visual modality. In fact, they're much better with odors in the olfactory modality. And much of my research has tried to capitalize on this and use odor stimuli in rats. You know, in fact, rats have more olfactory receptors even than dogs, and we know that dogs have very good odor perception. And rats have 4 times as many odor receptors as humans have. So in our laboratory, we've done a number of studies using odor cues, using manual procedures like this. We were able to demonstrate matching and non-matching to sample, generalized matching and non-matching in rats. And we've been able to automate these procedures in more recent years to demonstrate, again, emergent identity relations, generalized identity matching in rats. And this is the apparatus I want to talk about that we've tried to use now to try to replicate the Vaughan type procedures. So our first study, actually, it's just been accepted and it's now in press. It's a thesis that was conducted by Maddie Mason. And we basically attempted to replicate the Vaughan procedure with repeated reversals using this automated apparatus. So let me describe the apparatus a little bit for you. First of all, these jars are loaded up with odor-containing liquids, liquids with aromatic oils or other compounds. A pump forces air into the jar, and it's blocked from entering the operant chamber by these solenoid valves. When the computer operates and opens one of the valves, then that particular odor can enter into the operant chamber. So this tubing allows the odorants to enter into the chamber. It's a standard operant chamber. Notice there's a pellet dispenser in the rear. Now, if you look at the front, this is the way the chamber, front of the chamber looks to the rat. In all of the studies that I'm going to be describing to you today, we use only the center nose port for this. Now this port contains several features. First, there's a light here. This can be illuminated and we turn it on at the beginning of each trial. Second, notice that there's a photo beam. You can maybe see it more clearly here. There's a photo beam so that when the rat pokes his nose into this port, it breaks the photo beam and we record that as a response. So throughout the studies I'm going to describe today, nose pokes will be the operant response. Down here is a little aperture through which odors are presented. So when the odor is presented through this tubing, it comes out through this little hole, and you can't see it very well, but underneath here is also a little aperture, and we have a vacuum pump that pulls the odorant out of the chamber during the intertrial interval. So here are the procedures that we used in the Mason et al. Study. Each trial is initiated with the onset of the house light. That's up here. So the house light illuminates the entire chamber. And that center port light also comes on at that point. Then we require on every trial that an observing response, the animal has to make a single nose poke, and that initiates the presentation of the odor. If it's a positive trial, then sugar pellet reinforcement is delivered upon completion of an FI 5-second, fixed interval 5-second schedule. If it's a negative stimulus trial, then 5 seconds, a 5-second response period elapses, and then the trial simply terminates without reinforcement. Each trial is followed by a 30-second intertrial interval. All the lights go out during that period. Let me show you a little bit about how it works. So a typical trial would begin, the center port light and the house light comes on. When the rat makes an observing response, now we see, I guess this is blueberry odor emanating from the nose port. Reinforcement would be delivered after the completion of a fixed interval 5-second schedule. The animal can go to the rear of the chamber and pick up his sugar pellet. And then there's a 30-second intertrial interval. So what Mason then did was to train go, no-go, successive discrimination with 2 sets. Each set is going to contain 6 different odor stimuli. So we trained them to a criterion of a discrimination index of 0.7. So let's say initially we would present in the positive set cinnamon and in the negative set coconut. So responses to cinnamon would be reinforced. Responses when coconut is presented are under extinction. We would continue training this until the animal had reached a discrimination index of 0.7. That is, the S plus responses to S plus divided by total responses had to be 0.7 or higher. Once that criterion was reached, we would add 2 more stimuli, peach to set 1. Actually, we counterbalance the stimuli for different animals. But in this case, peach goes in set 1 and sandalwood, let's say, goes in set 2. When criterion was met there, we add 2 more. Bubblegum in set 1, clove in set 2, and then another, root beer and honey, apple, blueberry, and grass and rose. I have to tell you, we have the best smelling laboratory you can imagine. Now, we then would continue this. Now the animal is responding to 6 positive stimuli and 6 negative. When that criterion is reached with these 6 member sets, then we would perform a reversal. Now responses to the set 2 stimuli are positive and reinforced, and responses to the set 1 stimuli are under extinction. When the animal has met criterion after this reversal, we reverse it again, and we keep performing these reversals and re-reversals right on through the end of the experiment. This graph will give you an idea with the performance of one subject about how things worked. What I'm showing here is the discrimination index, the DI, across blocks of 12 trials. Each data point represents a block of 12 trials. So all of the 12 stimuli are presented in each block. And there's 5 blocks in each session. So, for example, this block will show the performance on the very last session of the final baseline session. So you can see when set 1 was positive, the animal met our criterion with very, very accurate performance, his discrimination index above 0.9. Now on the very first block after the reversal, as you might imagine, he's responding according to this with set 1 positive. Now set 2 is positive, and so his discrimination index is very low. But notice by the end of that first session, each one of these is a block. By the end of the first session, he's actually responding about 50-50. And at the beginning of the next session, he starts out, interestingly, responding pretty much equivalently to both set 1 and set 2. But then by the end of that first session, he's mostly responding to set 2. So he's beginning to learn the reversal. When he learns the reversal, we perform another reversal. And now he learns it again. It occurs a little more rapidly, as you can see. We do another reversal. You can see he's getting faster at it. But after many, many reversals, let's go down here. This is what the rat is doing after 22 reversals. I want you to notice some differences. He learns the reversed contingency very, very rapidly, but on block 1, this very first block on each session, almost every day, he starts out at about 0.5. So it takes him a long time to meet our criterion because he's got to be at 0.7 in all blocks. But the rats are just responding 50-50. They respond to everything at the beginning of every session, and then they learn which stimuli are positive very, very quickly within the session. And so this is just one performance of one rat, but it's very, very typical. So as we went through with reversing and re-reversing, we had difficulty. We began to find that we were not seeing much evidence of class formation. So we divided the animals into 2 groups. For one group, they received class-specific reinforcers. What we did there was when set 1 was positive, they continued to receive a plain sugar pellet. But when set 2 was positive, they received a banana-flavored pellet. We tried class-specific reinforcers because that seemed to be important in Kastak's sea lion studies. We thought it might be effective for our rats. An alternative strategy with the other animals, because these animals seem to be responding to all the stimuli equivalently at the beginning of the session, and that of course will prevent us from seeing class formation, we decided to shift the reversals to the middle or later on in the session. So we moved the reversals to block 3 for some of the rats. We ran these procedures for over a year, and all the minimum was 12 reversals. The most advanced animal received as many as 6 reversals. Again, and this was across 285 to 365 sessions. Here are the data for the 4 rats that got within session reversals. Let me remind you how to look at this. So here on the vertical axis is the discrimination index, and on the horizontal axis are successive reversals. And what you're looking at here, each data point represents the discrimination index on the very first reversal block. So this is the first time that the rat has encountered each of these scents after the reversal. What you might expect to see, since it's the first encounter after reversal, is that it would be the discrimination index would be very much below 0.5. If there were class formation, though, we would expect to see some evidence of above 0.5 responding. If there was good evidence of class formation, the DI should be up here, close to 0.8 or 0.9 anyway. But as you can see with this rat, it's not. It's right around 0.5. Every one of the reversals that in the first 6. And then here in phase 2, we started these within session reversals. It didn't help at all, did it? He's still responding right at 0.5 on the first block. Well, these results, as you can probably already see, are pretty similar for every rat. Q14, he started out below 0.5, but very quickly showed discrimination index of about 0.5 across every reversal, and similarly after we did the within session reversals. We got excited about Q15. We saw this data point, and then we were disappointed. And then these two, we were very excited, but you could see that the slight tendencies toward class formation that you see here above 0.5, they were not maintained. And when we went to the within class session reversals, well, again, pretty much 0.5. Again, a couple of interesting data points, but overall, no evidence of class formation for this rat. Similarly, you can see Q16, very similar outcomes. He's right around 0.5 throughout the entire experiment. We were very disappointed. But what about the class-specific? We had 2 animals that we trained with class-specific reinforcers. That worked pretty well for the sea lions. What about rats? Not so much. Again, these are the same graphs. You're looking at the discrimination index across successive reversals. And in phase 1, rat Q17 showed below 0.5 for his first 5 or 6 reversals. Then he's right around 0.5. Couple of data points got us a little excited. And boy, when we put in the class-specific reinforcers, we were very hopeful this might be maintained, but as you can see, it was not. So, and then with Q18, we really just didn't see any evidence of class formation at all. So these results were very disappointing. We found no evidence of class formation after as many as 285 to 365 sessions of training with multiple reversals. But we reasoned that this pattern of responding that I've described to you, where they would respond equally to both stimulus sets at the beginning of each session, but then very rapidly learn the discrimination as the session continued, we were a little puzzled about that. Now, one possibility is for each of these 12 stimuli, every session, they learn which stimuli are positive for each of the 12 stimuli completely independent. But another possibility, at least we thought was worth considering, maybe there were some stimulus relations that had been acquired and they were helpful or helping the animal to produce within session, this very rapid within session acquisition. So we did one more experiment with these rats. We performed what we call a set shuffle procedure. We arbitrarily rearranged the stimulus sets on the very last reversal session. So these were the original sets: cinnamon, peach, bubblegum, root beer, apple, grass. We simply arbitrarily rearranged them like this. So now coconut is in set 1, peach is in set 1, you know, half of the set 2 stimuli have been moved to set 1 and vice versa. Now, these stimuli had no history of association with a common outcome after the set shuffle. However, that should not matter if the reversal learning is occurring independently for each individual stimulus. So, is it or not? We tested the rats on the shuffled sets until they reached a criterion of 0.7, DI of 0.7. And here's the results. What you're looking at here is the number of sessions it required each rat to reach the 0.7 discrimination index criteria. And the black bars show how many sessions it required after the set shuffle. The gray bars show the average number of sessions required to reach 0.7 during the final 5 of the regular discrimination reversals. So if you look at the leftmost animal, Q12, he actually failed to reach a criterion of 0.7 after 10 sessions after the set shuffle. But notice he wasn't very good. This was our poorest learner. So he wasn't very good at learning this after the regular reversals. We see no differences. But in the remaining 5 animals, you can see pretty clear differences between their accuracy on the set shuffle. This animal never met criterion after 10 sessions, but he met his average was about 4 sessions on his last 5 of the regular reversals. Q15 took him 6 sessions after the set shuffle. His average was 2 before that. Took this rat 9 sessions to meet criterion after the shuffle. His average was about 3 before that. This guy took about 10, but his average was 3 before that. And this rat's averaged 1 session to meet the criterion, but after the set shuffle, it took him 6. So all 5 of these rats were showing some sort of interference in their reversal learning after the set shuffle. Here's another way of looking at these data, and this shows just their performance on the very first session, the set shuffle session. So what I'm plotting here is, again, discrimination index on the vertical axis and trial blocks in the first session on the horizontal axis. Let's start with rat Q12, our slow learner. He shows very similar acquisition across the session, whether there's a set shuffle or not. He starts out at about 0.4. He never gets very accurate in a single session after the set shuffle, which is the white circles, or after this is the mean of his last 5 reversals, the black circles. But the other 5 rats do show a difference in most cases. So Q14, you can see on a typical reversal, he starts at about 0.4, but he gets up close to 0.8, shows a nice gradual acquisition during the session. On the other hand, after the set shuffle, he doesn't seem to learn it. Q15 is beautiful. He starts out at about 0.4. By block 3, this rat is up to like 0.9, and by the end of the session, he's almost perfect. But after the set shuffle, really no evidence of acquisition. Q16 is similar. Nice acquisition during the course of the session, during the regular reversals, but no evidence of acquisition after the set shuffle. Q17 looked like very similar acquisition, but he did get a little better by the end of the session during regular reversals compared to the set shuffle. And then finally, rat Q18 shows this beautiful acquisition function after the regular or typical reversals, but after the set shuffle, he fails to learn. So this led us to the following conclusions. Using the Vaughan procedure and the Vaughan index, we saw very little evidence of functional classes after repeated reversals. But when we shuffled the stimulus sets, both within and across session acquisition was impaired, really in 4 out of the 5 rats. I'm sorry, 5 out of the 6 rats. And that suggested that the classes that were formed during the experiment, and that somehow they were interfering with the animal's learning of these shuffled sets. So our conclusion from Mason et al. Is that functional classes, in fact, may have developed, but they remained latent during our repeated reversals, maybe because of this pattern of indiscriminate sort of trial and error responding that developed at the beginning of each session and when encountering reversal. That led us to a second experiment, or really a set of experiments that I want to describe now. We reasoned that we needed to refine the procedures if we were going to be able to more clearly measure functional classes using these procedures. So in 2 theses, master's theses by John Shaw and Kendra Lawson, we developed what we call a stimulus presentation delay. In essence, we're continuing to do these repeated reversals, but on the day of a reversal, we simply withhold one member of each of the sets. These withheld stimuli then were introduced late in the session after the animals had begun to learn, had begun to discriminate the new reverse criterion. So here's how it worked. Let's say you've got 2 stimulus sets. This animal with set 1 stimuli are being reinforced on a particular trial. In this case, it's clove and peach and so on. And the set 2 stimuli are under extinction. They're S-. We required that they meet a criterion of 0.75 DI with blocks 2 through 5 in the session, and they had to do that for 2 consecutive sessions in essence. Once they met that criterion, we would perform a reversal. But now it's going to look like this. Now set 2 stimuli are positive, set 1 stimuli are negative. But notice we're only presenting, for the first 50 trials, these 5 of the set 2 stimuli. So they're going to encounter reinforcement with brandy and strawberry and vanilla and cinnamon, and they're going to encounter extinction with clove and peach and bubblegum and honey and blueberry. But after the 50 trials where they're receiving the reversed contingencies with set 2 and set 1, then we introduce the probe. We've held these 2 stimuli back. Root beer comes and peach during the 5-10 sessions. Now, root beer is a member of set 2, but it has not encountered the reversed contingencies. The rat has not encountered the reversed contingencies with root beer, and so no reinforcement with root beer until we present it now. No extinction with peach until we present it now. So we exposed these rats to 10 or more regular reversals. All the rats were exposed to 12 reversals with this 2 stimulus delay probe. and an additional 3 rats, we withheld 4 stimuli. So I have some 4 stimulus delay probes that I can show you also. The critical question here, what will the discrimination index be on the very first presentation of these withheld stimuli? We need to see it be above 0.5 to demonstrate stimulus class formation. If it is above 0.5, that would be evidence for transfer of function across functional class members. So here is the outcome for one rat, rat G10. I'm going to show you 3 graphs here. The first is his performance on the total block 1. That includes the first presentation for all 12 of the stimuli. And notice it looks very much like what we saw in the Mason study, maybe a little bit more evidence of class formation. There are a few data points after reversals that are above 0.5, but much variability, no consistent evidence of class formation. But now look at what we see with the 2-cent delay. That's going to be shown with these open triangles. And what you see here is the first 2-cent delay probe was very disappointing, but then we had 2 that were 0.9, then one that was about 0.5, but then the final 8, every one of them was above 0.5. 4 of them were actually 1.0, and that is on these 4 probes, the animal allocated all of his responses to the positive stimulus and responded 0 to the negative stimulus. So this seems to be some pretty clear evidence of class formation with the 2-cent delay. We went on and conducted another 12 probes where we withheld 4 odors, brought them in only at the end of the session. And here's what we got. Those are the open squares. Again, in this case, every one of these probes was at 0.5 or higher. Some of them, particularly the last 5 here, were very strong, almost perfect. So you can see the last 5 show really nice evidence of class formation. And our conclusion, both with the 2-cent delays and with the 4-cent delays for this particular rat, we believe that this is evidence of transfer of function. Now here's how it looked for 5 of the animals. One animal did not learn this procedure, failed to produce many reversals, and so alas, he's omitted from the data. But for the 5 animals that did complete the experiment, here's rat G8. This animal only experienced the 2-cent delay probes, and as you can see, his first few showed a lot of variability. His first one looked pretty good, but then, whoa, way down here, this one was 0.5, but his final 9 probes, every one of them was above 0.5. Most of them were really close to perfect, so almost complete discrimination. We consider this to be evidence for class formation. Rat G9, again, his overall probes, this is kind of interesting. He started out well below 0.5, came up to chance at about here, and then just bounced around a lot. But if you look at his 2-cent probes, 2-cent delay probes, all of them were above 0.5. 6 of them were a perfect 1.0. Most of them were well above 0.5. And his performances were similar with the 4-cent delays. All of them above 0.5, most of them very, very high discrimination indices. G10 is the rat that I described to you earlier. You could see his excellent performances on the 2-cent and the 4-cent delays. The 4th rat, G11, showed a lot of variability. It was a little disappointing. Some of his 2 stimulus probes were perfect, but some of them were right around 0.5. And indeed, if you look at his last several, he appears to have been losing the functional equivalence classes. But when we went on and did the 4-cent delay, his first one, again, it looked like he was losing it, but his last, really his last 11 probes, most of them were above 0.5, in the range of 0.8, one of them was perfect. So not as strong as with the first 3 rats, but at least some evidence of class formation for rat G11. And finally, G12, again, not quite as strong, but yeah, 9 of his 12 probes were above 0.5. Some evidence for class formation here. One more way of looking at these data, these are the actual response rates, the mean response rates on the first probe trials only for the 2-cent delay. Here's for these 5 animals, and you can see response rates to the positive set, that's in black here, were not only higher than for the negative set, but statistically significantly higher. We used a Wilcoxon's sign ranked non-parametric test. Dramatically so for G9, for G10, at least statistically significantly higher for G11. G12 was not statistically higher, but P was 0.06 for him, so pretty close. In any case, all 6 rats show at least some evidence for more responding to the positive probe trials than the negative probe trials. This was dramatically true for the 4-cent delay also. Each of them showed significantly higher responding on the positive probe trials. So some conclusions. I'd like to make the claim that these are the first demonstrations of functional equivalence classes in rats, at least using the Vaughan repeated reversals procedures. We're pretty excited about this because I believe these findings open up the possibility of studying symbolic behavior in rats, and therefore provide a valuable model, not just for behavior analysts, but I think potentially this kinds of procedures could have great value for neuroscientists as well. But there are a lot of questions that need to be answered. For example, will class expansion occur? Class merger? Will novel functions transfer across these classes? And in general, will the other properties that we see in equivalence classes with humans, can we measure these same, can we obtain these same properties in these classes with rats? I think answering these questions will make a very important research agenda. And so that at the end of the day, to Steve Hayes, I would have to say this: I believe animal research may yet prove to play a central role in the study of complex stimulus relations and equivalence classes. So thank you very much. I want to thank all these wonderful lab students. This is our incredible group of students that performed these experiments, and muchas gracias ustedes también.
Thank you very much. So we have here some questions and commentaries for your presentation. I will try to put together some of them. One is it's interesting that Mr. Murray-Sidman was against the use of the term function transfer or transfer of function.
Yes.
Apparently, now it's different. If the question if the theory changed or something changing the time.
That's a great question. You know, Sidman's theory, or in Sidman's theory, transfer of function is unnecessary. It's not a term that is needed at all, because by definition, the function, the response, is part of the class. It's a class member. Remember, in Sidman's theory, all of the elements of the contingency become class members. So that includes the stimuli, and of course that's what we usually study, but it could also include the response, if the response is class specific, as well as the function or the outcome as well. And so from Sidman's perspective, transfer of function, it's not incorrect to, I don't think he would say it's wrong-headed to use the term, but it's unnecessary because according to his theory, the observation of transfer is a given because that response is a class member. So you're simply measuring class members, not necessarily transfer. So I'm using the term transfer perhaps not to describe a process, although other theorists might disagree with that. But at least from Sidman's perspective, it's not a process. It's simply describing a phenomenon. I hope that answers that question.
Okay, perfect. Thanks so much. A procedure question in the when you use the notebook.
Yes.
The procedure is a free operand or is by trial, discrete trial procedure? The question is if you use a free operand procedure.
Yes, it's in fact the schedule. It's a fixed interval 5-second schedule. So once the response period begins on a positive trial, the first nose poke after 5 seconds is reinforced. Now, admittedly, you know, it is a kind of a discrete trial, but once the trial begins, it's a fixed interval 5-second schedule. Yeah, it's a discrimination procedure with a long intertrial interval. Let me explain that long intertrial interval, it's a 30-second intertrial interval, and the reason it is so long is so that we can vacuum out all the residual odors. We find that if we don't have we want to have short odor presentations and then long intertrial intervals so that we can eliminate the odor molecules on each trial. We've tried it the other way and it becomes difficult for the rats to discriminate.
Okay, thank you. And another question, first, a commentary that thanks so much for your presentation. And the possibility that the lack of consistent findings on equivalence in non-human beings, if that could conduct to forget the procedure of matching to sample or their derivatives?
I'm not sure if I understand the question.
Is the possibility that the matching to sample procedure is not exactly the best way to study the equivalence in non-human beings?
Absolutely. I think that is a conclusion that I've come to, at least with rats. You know, the studies I mentioned, that one that's in press and then Pritchard et al. 2015, even though these studies used a successive conditional discrimination procedure, they did use an arbitrary matching to sample procedure, and we absolutely failed to find evidence of class formation in those studies. In contrast, using these sort of concurrent simple discriminations, again, this is the first, I think, real strong evidence for class formation that we've been able to see in rats. So yes, I think I don't know about other species, but at least in rats, I think conditional discriminations are probably not going to work.
Okay. Un commentary about the procedure is is this long intertrial interval a control of olfactory habituation?
Well, that's a good question too. We think it's helpful for that because, as I mentioned, we have done some experiments with longer odor presentations, and the animals have difficulty with such discriminations. I don't know if that's because, the problem with odor discrimination is humans can't smell these odors. So I can stick my head in the operant chamber and I can't smell any residual odor. But even if there's a few molecules, the animal might be able to detect it. So one possibility is that the long odor presentations cause problems because of habituation, and there is odor, there's dramatic, as you probably know, habituation in odor perception, but it also might be that we're just not getting enough of the odorant out of the chamber. Yeah, but short presentations work best, yes.
Okay, right. Another question is about considering this kind of symbolic behavior you find. Could these results have obtained, could be related with any other kind of animal studies, for example, categorization tasks made by Edward Wasserman, for example?
Yeah. We're really interested in Wasserman's work, and some of the studies that Ed Wasserman and colleagues, Tom Zental has done some work that I think shows functional equivalence certainly in pigeons, and Zental I think has got some studies that I think are convincing in rats. They don't use the Vaughan type procedure, so they don't really show us class membership. And so some of the phenomenon that we want to look at, if we want to model Sidman equivalence, you can't really, or we haven't been able to devise ways of doing that using Zental's or Wasserman's procedures. But yeah, they've done some lovely work with concept formation, and I think functional equivalence in pigeons and rats. Nakagawa has done some work that you might be familiar with also. Yeah.
Okay, thank you. Well, there are some congratulations, commentaries for your presentation and for all your work. We are happy with your acceptation for this closing conference.
I only wish I could be in Mexico with you.
Oh yes, approximately. Maybe it's possible to have a face-to-face conference. It will be better.
Yeah, I hope so, and I hope I'll see you all in Boston, perhaps in May.
Perhaps in Boston next year. It could be. Yeah. Well, with this conference, we close officially the SINCA event. Thanks so much for your patience on this event. Thanks so much.
Muchas gracias.
Muchas gracias, Mark. Abrazos.